In previous videos, we've introduced Kirchhoffs laws, but that was in a fairly generic way. Here we're going to revisit them, but with an eye to doing application to electric circuits. So the first of them that we'll revisit will be Kirchhoffs junction law, or it's also known as his node law. So in his junction law, if you say have some connection between a few wires, now to make this a little more practical, that are carrying currents, let's say this is current number 1, and we'll make this current 2 and current 3. Kirchhoffs node law says that the sum of the currents going into a node or a junction is equal to the sum of the currents going out of a node or a junction. And what you'll have to do with this is case by case, every time you look at a node that you want to analyze, you'll have to look at the currents that were assigned in and the ones that were assigned out. So here we've got I1 that's inbound, so this would be the only the only inbound current. And here both I2 and I3 are outbound, so we'd write equals I2 plus I3 in this example. Now, in some other case, we might have more terms on both sides. We will be seeing examples of this as we go along. And you'll also notice that I said an assigned direction. This is because a lot of times in practical application of Kirchhoffs node law, we don't actually know which way the current is flowing until we've done the math. So a lot of times what you end up doing is taking your best guess. And if you get a positive number, that means you guessed right about the direction. And if you get a negative number, that means you guessed wrong about the direction. And that's really not the end of the world. You don't have to go back and redo the problem or anything like that. If, say, I solved for this and I got that I3 was negative 2 amps, I would just note that that meant 2 amps inbound. Or if I solved for this and got that I1 was negative 7 amps, that would mean that was 7 amps outbound. It would just mean that if I get a negative current, it just means that's opposite of what I guessed it was. So when you do these things, you should always be drawing your junctions and labeling your currents. And we've also seen his loop law, which is also known as his mesh law, depending on what book you want to look in. And so this just said, if I look at a bunch of points of interest that make a loop, and I add up all the changes in voltage around the loop, that would equal 0. Now, what this is going to mean for us in practice is we will pick a point in our electric circuit, and we will go around in a loop and get back to the original point. So clearly, the potential at the point is whatever it was, and if we go all the way back around, it's that same number. So the change in voltage had to be 0. And because the electric force is a conservative force, we've seen that no matter what path you take to connect any 2 points, you should always get the same route. So it doesn't matter whether I went through a bunch of electric devices on the way, or I just imagine staying put at that one point on the loop. So let's go and think about how to do that practically. So what we're going to be imagining is going around a loop of electric devices, and I will do some examples of how to set up loop law equations in just a second. But we have to think about how we're going to assign signs to this as we do it. So I always envision is when we're going along on a journey around a loop, I'm envisioning this like I'm walking my dog. Now, of course, my dog is more metaphorical than anything because I've got serious allergies, but we can imagine that I was metaphorically walking a dog. So this is just the direction that I'm traveling as I'm metaphorically walking my dog around the loop. This doesn't have anything to do with which way the electric current is actually flowing. This is just how I'm going around the loop. So here, if I get to a battery, so I'll have an EMF source here. In this example here, as I'm walking along, I first come to the negative terminal of the battery, and then I leave at the positive terminal of the battery. Now I remember that a battery does non-conservative work to move charges from where they electrically want to be to where they electrically don't want to be. So when I leave the positive terminal of the battery, the voltage increased by the battery EMF. And so if I'm walking in this direction, I would say that I would write a plus E when I'm doing my sum over delta V's here. On the other hand, if my travel direction were the other way, if I go from here to here, I'm going to where the charges want to hang, where positive charges would want to hang out. So that would correspond to a decrease in voltage, and that would be minus the EMF. So the sign that you put in front of the EMF is the sign of the terminal you leave. So here as I'm walking along, I leave the positive terminal, so I write a plus sign. Here, if I'm walking along this way, I leave the negative terminal, so I write a minus sign. And the other one to look at just for the moment is a resistor. Now with a resistor, what matters is the direction of flow of the assigned current. So let's just say we are assigning the current as flowing to the right. So again here, if I'm walking my dog along the resistor in the direction of conventional current flow, we know that the electric field inside the resistor points in the direction of conventional current flow. We know that that electric field lines run from high voltage to low voltage, so this has to be the higher potential side of the resistor. This has to be the lower potential side of the resistor, and so the voltage would have had to drop. And by how much? Well, twinkle, twinkle, little star, delta V equals I times R. And similarly, if I'm walking upstream, now this is still the high potential side, this is still the low potential side, so the voltage increased again by IR. So you use the minus sign if you're going downstream, and you use the plus sign if you're going upstream. All right. So let's just do a few practical examples of how I would write a loop law, and then we'll start to take a look at that to look at a real-world battery. So in the first example here, I'm going to just imagine that we have a resistor hooked up to a battery. Now, as always, make sure if you're going to build such a thing that you have proper supervision, and make sure that your resistor is adequately rated for the power that it's going to draw. There we go. So there's the battery EMF, there's the resistance R. This is positive terminal, negative terminal. In this case, because there's only one device hooked up to the battery, we already know that the current is going to be flowing clockwise through the circuit. This is because we know that conventional current in a battery flows from the negative terminal to the positive terminal. So it's just got to flow clockwise. So here I'm going to make the very lucky guess that it's flowing clockwise. Now when I do loop laws, and this is purely a matter of personal preference, and other people have other surefire ways of doing loop laws where they won't get lost. But when I do loop laws, I always start in the lower left-hand corner of the loop, and I walk clockwise. Why? Because when I was first doing these, I was getting confused about where to start, so I decided lower left corner. And I would get myself turned around about which way I was traversing the loop, so I just decided clockwise. There are plenty of other surefire ways of doing these things so that you never get lost, but I just simply decided that that was how I was going to do it, and it has served me well so far. All right, so now this is me we can just imagine I'm walking my hypothetical dog around this circuit block until I get back home. So as I walk my dog along by the battery, I leave at the positive terminal. So I would write plus the battery EMF. And then I keep walking my dog along. Wires have negligible resistance, so there's no voltage change. Then I get to my resistor and I'm going downhill, if you will, because I'm following the assigned current. So that will be a minus sign, IR, and I get back home. And whenever I get back home, I just write equals 0. So sure enough, I mean, it's what we expected applying Ohm's law in this case, but it's good to know that it works here. All right, let's try a more complicated example. And you certainly don't want to build this because wiring batteries in opposite directions can be a serious recipe for blowing things up. And so let's say I have 2 batteries head to head and 2 resistors. And for mysterious reasons, I am going to copy and paste it right now. And basically just stick another copy down there. Okay. So here, let's go ahead and analyze the circuit. Now in this case here, unless I know the voltages of the batteries, I'm not entirely sure which way the current's going to flow. So here I'm going to just assign the current flowing clockwise, which will turn out to be the case if E1 is bigger than E2. So that's what I'm assigning. And then I'll go ahead and draw in my loop. So I'll be walking my hypothetical dog around the loop, starting at the lower left corner and going clockwise. Again, just because that's how I roll. If you ever run across some other way to do it, or just you think of some other way that makes sense to you, then do that. So walking my hypothetical dog along, I exit this first battery at the positive terminal. So this would be plus E1. And then I exit at the negative terminal with this at the second battery. So that's minus E2. Here I'm going downstream, so I'll say minus IR1. And I'm going downstream here, so I'll say minus IR2. And then I'm back home, so I write equals 0. Now, what if E2 were bigger than E1? In that case, the current would be flowing the other way around. So here I'll go ahead and assign the currents the other way around, but I'm still going to doggedly, no pun intended, walk my hypothetical dog around clockwise like so. And actually what I would like you to do at this moment is to pause the video write down Kirchhoffs Loop Law for this situation, then unpause it, and I'll get back with you. Alrighty, so what do we get? Well, again, the direction of the current through the battery doesn't matter. Whoops. The direction of the current through the battery doesn't matter as far as assigning voltages go. Just the terminal that you're leaving. So here, as I walk my hypothetical dog along, again, I'm exiting E1 at the positive terminal. So I'd still be writing plus E1. And same deal here, I would be writing minus E2 because I'm leaving at the negative terminal. Now in this case here, if the current's really flowing counterclockwise, E2 is bigger than E1, and this will be a negative number, but they'll be okay. All right, continuing to walk along, I will be going upstream at R1. So if I go upstream, that's a plus IR1. And similarly, I'm going upstream at R2, sorry, plus IR2. And then I get my hypothetical dog back home, and I write equals 0. Now I had alluded that if the current really is flowing counterclockwise, it's because E2 would be bigger than E1. So that would make that a negative number. But then if I add that to both sides, I'll have a positive number over here. R1 and R2 are positive, so I is a positive number, meaning that we would have guessed right. But again, even if we guess wrong, it's not the end of the world. We just get negative answers for the current. So let's go ahead and do a more practical example of this and take a look at what happens if you have a real battery. So with a real battery, like I've said before, the ions traveling through the battery, so let's make this the positive terminal here. That's the negative terminal there. Within a battery in normal operation, so we'll say the current is flowing like this. In normal operation, what you'll have is both positive ions drifting up, but you'll also have negative ions drifting down. And all of these ions are going to collide with just stuff that's in the battery. So that's going to create resistance. And that's just plain unavoidable. So the way we can model this, though, turns out that we can just replace this mentally with an ideal battery, an ideal EMF source in series, so just connected directly to its internal resistance. And we usually use lowercase r when it's an internal resistance that we're modeling. And this is because although it's big enough to worry about sometimes, it's usually smaller than other things in the device. Whoops. And so then probably you'll have this attached to some sort of external load, like so. So now let's go ahead and take a look at this. So now if this is discharging, just the normal state of operation for a battery, if you have a discharging system, the current is going to be going from negative to positive inside the battery. So if I want to look at let me just draw it like this so that we're less confused. My apologies. There we go. So let's just take a look at a little stub of our idea of our real world battery here. So let's say we're discharging. So that would look something like this. Now, if you measure the terminal voltage of this, and we're pulling current this way since we're discharging. If you measure the terminal voltage, you would be sticking the red lead here and the black lead here. There we go. And so the voltage you'll read will be the voltage at this point minus the voltage at this point. So even though this isn't a walking back and getting home, we can still add up the voltage differences here. So delta V would be, if we assign the black lead to be 0, what we get? We increase by the battery EMF, and then we decrease by I times little r. And so the terminal, so this will end up being the terminal voltage, which is what a voltmeter would read. So this is the voltage at the red lead minus the voltage at the black lead. This is the number that a voltmeter would read. And you'll see that it'll be less than the battery EMF. Now, if you're charging, actually, let me just slide this all down. There we go. Now, if you're charging, which is not the typical case, but hey, you plug in your cell phone every night, right? If you're charging the battery, what's happening with a rechargeable battery, and we do need to be careful about where the term charging is coming from. We'll get to that in a second. In a typical rechargeable battery, what's happening is you attach it to a power source, and you literally are driving current through it the other way. This is still going to be what the red lead reads. So where you put the red lead. This would still be where you put the black lead on the meter. There we go. So here, the terminal voltage that you read will be we increase by the battery EMF, but now because I'm going upstream, it'll be plus IR. So the terminal voltage when you're charging a battery will be greater than the battery EMF. So about the word charging, this is where a lot of sources of misconceptions about batteries come about. As we've already seen, all batteries do is just move electric charges from one side to the other. The actual net electric charge in the battery is 0. You have just as many positive as negative ions at all times. That never changes. We just move them around in order to keep shoving charges around a circuit. But sometimes people get a little confused on this idea, and it comes from where these words charging, discharging came from originally. Think about using a fire extinguisher. If you use a fire extinguisher, you discharge it. That's the word we use for that. And believe it or not, when fire safety companies come around and they service fire extinguishers, usually what they do is they weigh them and they make sure there's enough chemicals in there, and they check the date to make sure that certain chemical reactions might not have occurred and stuff like that. If they decide they need to put more chemicals into the fire extinguisher, like say you discharged it, they call that charging the fire extinguisher. And so the term charging, discharging has its origins in adding or removing chemicals. So a way that you can charge a battery is to add more chemicals. In old style lead acid batteries, this is sometimes literally done by adding more acid to the battery. For instance, the kind of batteries that get used in battery backup systems for sump pumps. I mean, when is the basement going to flood? Probably when you had a power failure, right? So, because why do you have a power failure? It's because you have a big storm happening, so that's when your basement's going to flood. That's when you need your sump pump to kick on. And if you have a power failure and your sump pump isn't kicking on, then you're going to have yourself a wet basement. So to protect against that, a lot of sump pumps, will come with these very hefty batteries that are heftier than the typical car battery. And usually about every year and a half, something like that, you'll have to actually go and charge the battery by going and by opening it up carefully, and trust me, wear your oldest, rattiest clothes, because otherwise they will become your oldest, rattiest clothes anyway. And you carefully add the acid into the battery. And by so doing you charged the battery. You gave it more chemicals. In the era of rechargeable batteries, how are you giving it more chemicals? Well, by running the current backwards through the battery, it turns out that for the particular chemistry at hand, you're just causing the reverse chemical reaction to happen. So when you were discharging it, you had reactants turning into products during the chemical reactions within the battery. And when you charge the battery, by running the current backwards, you are taking those products, running the reverse chemical reaction, and creating reactant again. So in that sense, you're charging the battery because you have created more chemical. Alrighty, so let's just do a quick example of this. So if you remember this photo that I showed you last time, where we had two batteries hooked up in series, and you can see I got a voltmeter attached across the batteries reading 2.73 volts. And then I have an ammeter wired in series with the two batteries. The voltmeter is attached in parallel to the battery. And the ammeter was attached in series to the battery and light bulb, and we measured 66.9 milliamps going through it. Now, I took that same pair of batteries and I measured the voltage of the batteries without a load, and it turned out to be 2.92 volts. And without a load, that would be the battery EMF. So with that information, let's go ahead and calculate what the internal resistance of the battery would be. So we have that the terminal, we're discharging here. So we have that the terminal voltage will be the battery EMF minus I times little r. We want to solve for little r, so we need to do a little bit of algebra. Whoops. My bad. E minus delta V. So then little r is E minus delta V over I. So I measured the battery EMF to be 2.92 volts minus 2.73 volts was the terminal voltage that we saw in the picture. Then 66.9 milliamps is 0.0669 amps. This turns out to be 2.84 ohms of resistance. By comparison, the light bulb had a resistance of 40.8 ohms. So, about 7% of the resistance of the light bulb. So it's not negligible, but it is small. Alrighty. So I'll finish this off by taking a look at power considerations. So remember, power is the rate at which we transfer energy. So the power that's delivered by an EMF source, say your battery, so the rate at which energy is being transferred. This will be equal to the change in the electric potential energy as a function of time. But by the definition of EMF, this will be however much charge went through in that amount of time times the EMF over that time. Hey, that's the delta Q over delta T. That's the current. So we get that the power that's delivered by an EMF source to a circuit is the current going through the EMF source times the EMF. Now, what about the power dissipated by a resistive device? We'll call that P sub R. Well, again, it's the same deal. It'll be the time rate of change of the electric potential energy. So this will be in that amount of time, so amount of charge delta Q would have gone through a potential difference delta VR. This is over delta T. Again, that's the current. So it is always correct to write that the power dissipated by a resistive device is I times delta V. Now, if the device is ohmic, we can use twinkle, twinkle, little star, delta V equals I times R to give us that it's also I squared R or delta V squared over R. And honestly, I use all three of these roughly equally. So let's just take a quick example of this. Let's think about a hairdryer. If you go and take a look at a lot of travel type hair dryers, and I'm sorry for making you have to look at my horrible artwork. You got some sort of a switch there. You got the big fanny thing here, and then this is where the air goes out. And so you know this is this horrible drawing as a hair dryer because I labeled it as such. Anyway, one thing that you may or may not notice is in a lot of these, there's a little switch that gets somewhere on there that will say 110 on one side of the switch and 220 volts on the other side of the switch. And so the idea is you're supposed to put the toggle at whatever the operating voltage is in the country that you're using it in. So if you are in a reasonable amount of the New World or Japan, you're going to throw this switch over to the 110. And if you're in Europe, you'll throw this switch over to 120. Now, what inevitably happens, say, if some American takes a hairdryer with them on a trip to Europe, now, of course, it doesn't happen to everybody, but it happens to enough people that it's a bit of a meme. These hair dryers are typically on the order of 1,500 watts. So this means that they deliver 1,500 joules of heat every second to your hair. What happens is they bring along the little adapter that changes the shape of the plug from an American style plug to a European style plug. And so they just plug the American plug into one end of the adapter, and then the other side goes into the outlet in Europe. But they forget to throw that 110-220 switch. So let's figure out the rate at which you are emitting heat in this case. So here, what we don't know is we don't know the resistance of the hairdryer, but we also know that it isn't going to change whether I'm in the US or the EU if I don't throw that switch. The electricity is going through the same amount of high resistance wire. So what we can do is we can set up a proportion. We can say the power emitted by the hairdryer in the EU over the power emitted, say, in the US. Well, this will be the voltage in the EU squared over R, and then this will be the voltage in the US squared over R. And since we didn't throw the switch, it's still the same hairdryer. The resistance doesn't change, so we can cancel that. So we can clean this up a little bit and get that this is delta V in the EU over delta V in the US squared. So if I don't throw this switch, the power that my hairdryer will try to emit in the EU, so it'll do in the US times the square of the ratio of the voltages. So again, a typical hairdryer is 1500 watts, unless you're talking about one of the really super crappy hotel ones that don't dry anybody's hair. So this is 220 volts here up to 240. This is 110 volts up to 120, somewhere in there. So we'll just use these numbers squared. Well, this is just 2 squared is 4. 4 times 1500 is, holy cats, 6,000 watts. And so the usual end point of the legend is that the person's hairdryer melted down. Now, why doesn't this happen when you plug in other devices? Well, when you plug in other devices, like computers or stuff like that, they don't draw anywhere near as much current as a hairdryer. So it turns out what they can do in the power supplies is they actually just have a voltmeter built in. The very first thing it does is it measures the voltage of the plug that it's hooked into, and then automatically reconfigures itself if need be in order to properly operate with the local voltage. With a hairdryer, though, that doesn't work. The currents are too high. Those auto switching devices can't be made affordably. So they rely on putting that switch on the hairdryer. And what it does is it actually causes the current to flow through a longer stretch of resistive wire, so that you increase the resistance fourfold so that you still have a 1500 watt hairdryer. Alrighty, so in the next video we will go ahead and take a look at combinations of resistors. So I hope to see you over there. Have a good one.